All right, so next we're going to look at stoichiometry of gases. I'm just going to give you one more problem that deals with stoichiometry of gases. Because really, all you're going to do here is, it really combines stoichiometry that we had in our previous chapter and also on our last exam with a little bit of new stuff that deals with STP volumes. So really, you realize that if you have mole-to-mole conversions by using a balanced chemical equation, and you can relate the volume to the number of moles, that we can go ahead and use volumes to convert to stoichiometry of a gas. All right, so let's look at that. So we're not really doing anything new here. We're just combining that last little concept of STP volume with the stoichiometry that we had in our previous chapter. So here's our example. So this is really nothing new. So we have an equation of just gases. Of course, you realize that if you do any reaction at very high temperature and pressure, very high temperature and low pressure, it's all going to be in gases. So you can write any equation really as a gas equation. But here's an equation that actually is a gas equation at normal conditions. All right, so the question asks, if you have a reaction at STP with 17.7 liters of N2 gas, assuming an excess of hydrogen gas, how many liters of NH3 will be produced? Okay, so there you are. There's the word problem. Stoichiometry of gases with STP volumes. So really, this is nothing new, so it shouldn't be surprising to you. You should probably be able to do this problem without me even going over how you do this problem, because all you do is you just add in that one last thing about STP, and it's the same problem that we had before. Okay, so let's look at what we have. You got it at STP, which is good, and then you have 17.7 liters of N2, so this is volume of N2. And you're asked for volume of NH3. And that's all you're given. So we're looking at this and we're trying to figure out what to do. All right. It does say at STP, and this is also at STP, so we can make some conclusions based on the STP. Okay. So what we know is that at STP, 1 mole of any gas occupies 22.4 liters. We know that to be true. All right. So we can say we don't even have to bother figuring out the number of moles, except that we need it for as far as the we don't have to deal with masses of things, because we can use liters as if we were using molar volume. A molar we can use our volume of gas the same way that we use our molar mass. So you can say that 1 mole of N2 gas is equal to 22.4 liters at STP. You can also say that 1 mole of NH3 gas is equal to 22.4 liters at STP. Okay, all we did there is we're just using the definition of STP. The other thing that we can get out of this balanced chemical equation is that 1 mole of N2 gas is equivalent to 2 moles of ammonia gas, according to our balanced chemical equation. And where am I getting that from? I'm just getting that from this. So this is just from your balanced chemical equation. The other two are just from the definition of STP for any gas. So let's look at this question and see. So this is basically going to be one of those dimensional analysis problems where you use all the stuff that you know to convert one from one thing to another. The other thing is, this is the amount that we start off with. So you got 17.7 liters of N2. And we're going to use that to get the liters of NH3. So what we're doing overall is we're going from 17.7 liters of N2. And I would like to figure out how many liters of NH3. So that's the overall thing that we're trying to do. We always start out one of these dimensional analysis conversion problems by the amount that we have. And how much do we have? We have 17.7 liters. We're going to go ahead and write down 17.7 liters of N2. Now what else do we have? Well, we've got this, but we can't use this yet because this isn't liters. But we can use this because we can use the liters to go. We can use the liters to go to this STP volume to go to moles of N2. And then once you get the number of moles of N2, you can use this to convert to moles of ammonia. And then you can use this to convert to liters of ammonia. So there we go. All lined up, pretty much the whole word problem all done. Okay, so we're going to start out with 22.4 liters of N2, and we're going to say that that's equal to 1 mole of N2 gas. Then we're going to use our stoichiometry, and we're going to say our balanced chemical equation. We're going to say 1 mole of N2 gas is equal to 2 moles of NH3 gas. Okay? And then finally, we're going to say that because we're trying to go from liters to liters, our final number that we're going to use for our dimensional analysis is, I'm going to say 1 mole of NH3 gas is equal to 22.4 liters of NH3 gas. Okay, so let's see what we've got here. We've got liters of N2 canceling out liters of N2. We've got moles of N2 canceling out moles of N2. And then we have moles of NH3 canceling out moles of NH3. And the only thing I end up with still left is liters of NH3. So there we are. So all we have to do is crunch the numbers through. And all we did is we just used our 3 conversion factors up there. We're just going to go ahead and crunch the numbers through, and we will get 35.4 liters of ammonia gas for our final answer. So we really could have done this without anything additional to that last little additional thing that I gave you about STP conversions, the mole to liter conversion. Other than that, this is just a general old standard stoichiometry kind of problem. So it really is pretty straightforward. We have 3 significant figures, 3 significant figures here. Those are definitions, so those have infinite number of significant figures, so we're good to go with that number there. Now, one additional thing that I would like to go over is using the ideal gas law to look at density. And I don't really think that this is a really important concept. I mean, I think the stoichiometry of gases and using STP is a very important concept because you end up using that a lot in general chemistry word problem kind of things. But the density of gases is is something that you're going to use in your lab that you're doing this week. So we're going to look at that equation. And we're going to derive that equation from the ideal gas law. So for this, I would say probably will not show up on exams and quizzes. It probably is not going to show up in the exam exactly in the kind of wording that I'm going to give you here. It's kind of an equation that you don't run into that often. So it will definitely not be on the quiz that you get on Thursday, but it is something that you are going to use in the lab this very week. So I'm going to go ahead and go over that. All right, so we have the ideal gas law that I gave you during this, I think the first part of this Tuesday lecture. So the ideal gas law says PV is equal to nRT. And you remember that N represents moles, and moles is equal to mass over molar mass. Right? Molar mass. So molar mass of whatever gas. Mass divided by molar mass gives you the number of moles. So I'm going to use the abbreviation, your textbook uses this. I'm going to use this. I'm going to use that script M. I'm going to say that that's equal to molar mass. So I'm going to rewrite the equation for moles as mass over script M. So there you are. And what we're going to do is we're going to plug in place of N, mass over script M, which is molar mass. So then this equation becomes, the ideal gas law equation with this substitution becomes PV is equal to mass over molar mass times RT. Right? Now, I'm not asking you to do this derivation. This derivation of the density equation out of the ideal gas law is probably not going to be one of the questions that you will be asked. But it is possible that you could come up with a need for this at some point. This is not likely to be a problem that you're going to get on the next exam. I'm just trying to get that sun out of my paper. I'm doing this next to a window, next to an open window, and the sun, I noticed, kept coming in. Okay, so there we are. And what we're going to do is we're going to do a little bit of algebra. So I'm not going to show you all the algebraic steps, and I'm not asking you to do the algebra steps. But we're going to do a little bit of algebra, to the point that we rearrange that equation. So we're going to do a little bit of algebra and rearrange equation to look like this. So the rearranged equation is going to be mass in grams over volume in liters is equal to pressure times script M, which is molar mass, times RT. Now, mass or volume, if you remember, density is mass over volume. Usually, we have mass density where mass is grams and volume is milliliters. But you know, there's no reason why you can't report it in grams per liter. It's just the same thing. It's just slightly different units. So we can actually make this, instead of milliliters, we can make it liters. And it actually makes more sense because gas volumes are so low that you really can't comfortably come up with mass and volume in milliliters. So then we can rewrite this equation where you plug in density. right there. So then our equation becomes density is equal to pressure times molar mass over RT, where density is in units of grams per liter. So there we are. Okay, so during the lab, you're going to use this equation. And what you're going to do with this equation is you're actually going to solve for molar mass. You're going to be given the density, or you're going to be able to find the density off of a chart that's in the on a little program in the computer lab. So you're going to get the density at a given temperature and pressure, and then you're going to get the pressure, you're going to get the temperature, you have the R value, and you're going to solve for the molar mass. So that's what you're going to do in the lab. Okay, so there we are. The quiz covers material up to, not including the density, not including this. This is not going to be on the quiz. I will never ask you for the derivation of density from the ideal gas law. That's not going to ever show up on the exam. But this last part is primarily just so you know what the equation is that you're using in your lab is coming from. But the rest of the material is perfectly valid for me to put on the exam, on the quiz that you will get on Thursday, where this is Tuesday's lecture. Okay, see you when I get back, and I think this is I honestly think this is one of the easiest chapters in the entire book. Okay, see you. Bye.